So in this example, we want to sketch the graph of f of x equals x cubed minus 7x plus 6. We want to follow the procedure outlined in the previous section. We're going to use synthetic division and the remainder theorem to find the zeros. Now, looking at our procedure from the previous section, to graph polynomial functions, we can use the leading term test to determine the end behavior. We can find the zeros of the function by solving f of x equals 0. And this gives us the x-coordinate of the x-intercepts. We can use the x-intercepts to divide the axis into intervals and then choose a test point to determine the sign of all function values in that interval. We can find the y-intercept by finding f of 0. If necessary, we can find additional points, and then we can use like the fact that we're going to have only the degree number of x-intercepts at most and the degree minus 1 turning points at most. We can also use multiplicity and a graphing calculator to kind of verify things. So using this process from the previous section, let's start by thinking about the end behavior, and we can do this from the leading term test. Our leading term is x cubed. So the coefficient on that is understood to be 1, which is positive, and we have an odd degree, 3. So the fact that we have an odd degree and we have a positive leading coefficient means that the end behavior is going to be down on the left and up on the right. So as x goes to negative infinity, y is going to go to negative infinity, and as x goes to positive infinity, y is going to go to positive infinity. Next, we're going to find the zeros and the multiplicity. Now, this is the challenging part that we would not have been able to do in the previous section because we did not have the tools for this. So we're supposed to use synthetic division and the remainder theorem to find the zeros. So this is kind of like our last example. We have the function x cubed minus 7x plus 6. Notice there's not an x squared term there, so we're missing an x squared term. And so we have to just kind of take a guess and try to find a zero of our function in order to be able to determine if we have a factor. Okay? So I'm going to pick just, again, a random sort of guess. I always like starting with like 1, 2, and -1, -2, and so on for easy sort of guesses. So I'm going to find f of 1 to see if it is a 0. And to do that, remember, if f of 1 is a 0, then x minus 1 would be a factor of our function, and I'm going to use synthetic division as we're instructed to try to determine this. So using synthetic division, I'm going to write down the coefficients of my polynomial function here. So the coefficient on the x cubed term is 1. We're missing an x squared term, so we're going to put 0 for that. The coefficient of negative 7x is negative 7, and then our constant is 6. And I'm going to see if f of 1 is a 0, and so I'm going to put 1 out here in order to check that. Okay? Again, if it is, that means x minus 1 is a factor. So using synthetic division, drop down my 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 7 plus 1 is negative 6. 1 times negative 6 is negative 6. 6 plus negative 6 is 0. So I got lucky. Okay? So what I have just found is that because I got a remainder of 0, x minus 1 is a factor of our function. So f of x, which equals x cubed minus 7x plus 6, will factor into x minus 1, again because 1's a 0, times, using this, 1x squared plus 1x minus 6. Again, I know it's x squared here because if I take x cubed divided by x, that would give me x squared. So that's where this next factor has to start. Okay? Now, x squared plus x minus 6, I can factor. Find two numbers that multiply together to be negative 6, that add together to be 1, and so that's going to be positive 3 and negative 2. So this factors into x plus 3 times x minus 2. And so our function factors into x minus 1 times x plus 3 times x minus 2. So our zeros are going to be 1, -3, and +2, and each of those has a multiplicity of 1. So all three of these have a multiplicity of 1 in this particular case. Okay? This also means that we have x-intercepts. Our x-intercepts are 1, 0, -3, 0, and 2, 0. So let's continue on the next page. So next we're going to create our table of signs. Now remember, we have found that the zeros of our function are -3, 1, and 2, which also gives us the x-intercepts. I've just rearranged them in order from left to right. And remember that our function is f of x equals x cubed minus 7x plus 6. So our zeros, our x-intercepts, divides the number line into 4 regions. So we're going to look at the interval from -infinity to -3. We're going to look at the interval from -3 to +1, the interval from 1 to 2, and then the interval from 2 to infinity. And we're going to choose a test value from each of those intervals to determine if our function values are positive or negative. So looking at the interval from -infinity to -3, we need to choose a test value, and -4 is a decent test value. So we need to find f of -4. And we can do that several different ways that we've learned now. In this case, I'm just going to substitute it in. So that's going to be -4 cubed minus 7 times -4 plus 6. -4 cubed is -64. Minus 7 times -4 is going to be plus 28. And then we still have plus 6. Now -64 plus 28 is going to be -36. So we have -36 plus 6, which is -30. So f of -4 equals -30. And what we really care about is that that's negative. And the significance of that is that the graph of our function is going to be below the x-axis on the interval from -infinity to -3. So when we're to the left of -3, the graph's going to be below the x-axis. Looking at our next interval, -3 to 1, we need to choose a test value. 0's in that interval, so I like to use 0 when I can for the test value. We need to find f of 0. So f of 0 is going to be 0 cubed minus 7 times 0 plus 6. 0 cubed is 0, 7 times 0 is 0, so 0 minus 0 plus 6 is just going to equal 6, which is positive. And the significance is our graph will be above the x-axis on that interval. Looking at the interval from 1 to 2, we need to choose a test value. Well, now this one's a little more challenging because there's no nice pretty numbers between 1 and 2, so we're going to have to use a fraction. So maybe I'll use the fraction 3/2. Okay, so we're going to need to find f of 3/2. So f of 3/2 is going to be 3/2 cubed minus 7 times 3/2 plus 6. 3/2 cubed is going to be 3/2 times 3/2 times 3/2, which is going to be 27/8. 7 times 3/2 is going to be 21/2, and that's minus. Again, think of like the 7 as being over 1. 7 times 3 is 21. 1 times 2 is 2. And then we still have plus 6. So to combine this, I'm going to have a common denominator, and that common denominator will be 8. So 27 over 8 is going to stay 27 over 8. But to change 21/2 into something over 8, I'm going to have to multiply the top and bottom by 4. So I'm going to have minus 21 times 4 is 84, and 2 times 4 is 8. And then thinking of the 6 as being over 1, I'm going to have to multiply both 6 and 1 by 8. So 6 times 8 is 48. 1 times 8 is 8. So I have 27/8 minus 84/8 plus 48/8. Now 27 minus 84, 27 minus 84 is going to be 57. So this will be, when I combine these, that's going to be negative 57/8 plus 48/8. And negative 57 plus 48 will be negative 9, so that's going to be negative 9/8. So f of 3/2 is going to be negative 9/8. Really what I care about is that that's negative, and so that means the graph is going to be below the x-axis when we're on the interval from 1 to 2. Last but not least, we need to find a test value for our interval 2 to infinity. So 3 would be a nice test value. So we're going to find f of 3. F of 3 is going to equal 3 cubed minus 7 times 3 plus 6. 3 cubed is 27. 7 times 3 is 21, so minus 21 plus 6. 7 minus 21 is 6, and 6 plus 6 is 12. So f of 3 is 12, which is positive, so our graph is going to be above the x-axis when we're on the interval from 2 to infinity. So we can use this information to help us with our graph. So let's continue on a new sheet. So our y-intercept. So we need to find f of 0, which we actually did as a test value on the previous page, and we found that that was 6. So our graph is going to be crossing the y-axis at 6. Now, we also learned on the previous page we had the zeros of negative 3, 1, and 2. So here's negative 3, here's 1, here's 2. So negative 3 zeros in x-intercept, 1 zeros in x-intercept, 2 zeros in x-intercept. We learned previously that the end behavior is going to be down on the left and up on the right. And we learned from our table of signs that when we're on the interval from negative infinity to negative 3, we're going to be below the x-axis, which this indicates with the end behavior. When we're on the interval from negative 3 to 1, we're going to be above the x-axis. So between negative 3 and 1, we're above the x-axis. So this graph is going to have to somehow come around. It's got to go through the y-intercept and then come back down so that 1 will be an x-intercept. Then between 1 and 2, the graph is going to be below the x-axis, so it's going to have to go down and turn around and come back up so that 2 is also a x-intercept. And then from 2 to infinity, we're going to be above the x-axis, so that's going to continue up, which we already knew from the end behavior. So our graph is going to look something like this. So there's our rough sketch. We can check this by using our graphing calculator. So if I bring in the graphing calculator, I already have the equation typed into the calculator. So if I try a zoom 6, I don't get the best looking graph, but it's not horrible. I can see that I have the x-intercepts of negative 3, 0, 1, 0, and 2, 0. I just can't quite see up high enough. I can also, by the way, see that the y-intercept is there at 0, 6. This is enough to know that my rough sketch is correct, but we can make this look a little nicer by, say, expanding our y-axis maybe from negative 20 to 20 with a scale of 2. And so that is a better looking graph which matches our rough sketch.